Hello everyone, so in today's video we're going to be discussing exponential growth and decay, which is section 6.5. So we just have a few definitions to start and then we'll jump into some example problems. So first we see here, if y of t is the value of quantity y at time t and the rate of change of y with respect to t is proportional, then dy dt equals ky for integer k in the real numbers. So if k is positive, then dy dt equals ky is natural growth, and then if k is negative, dy dt equals ky is natural decay. So those are pretty straightforward properties, but we'll be using those later on in a couple of examples. Now we know down here, the only solutions of dy dt equals ky are of the form y of t equals y0 times e to the power kt, where k is an element of all real numbers, and that's a constant, and then y0 is the initial value. And this can be manipulated to to like m of 0 or something else. So depending on the problem, this might change slightly, but it's always going to be something of 0, and that's representative of the initial value. So the first problem we're going to look at is the population of a yeast cell develops with a constant relative growth rate of 0.4159 per hour. The initial population has 3.8 million cells. Where is the population after 2 hours? So this is the key part of this problem right here, is the constant relative growth rate of 0.4159. So it must be constant in order to apply the definition we talked about earlier. So we remember over here we had y of t equals y0 times e to the kt. We're just going to manipulate that here. It's going to be the same exact equation, but just written slightly different, equals p of 0 e to the kt. So we're just changing the variables to be more representative of this problem. So this time it's p, that means population, with respect to time. So that's the formula we're going to use. And we know the initial population that we're given is 3.8 million. Remember, I said that was representative of initial. So therefore, we can say P of t equals 3.8 times e to the k, that's the rate. So I'll just label all these actually. So that's going to be the rate, and then that's the time. So the rate is 0.4159, and then we want to know population size after 2 hours, so plugging in 2 for the rate. And then you can just check this with the calculator. P of 2 rather for 2 hours equals 3.8 e to the 0.8318. That's this term here multiplied together, and then completely simplified, this would be 8.7 million cells. So if you have a calculator, this would be the final answer to get to. However, if you wrote something like this here or this here, either of these would be acceptable also. And that's just a simple example of relative growth rate. For this next problem, we're going to be looking at a bacteria which grows at a constant rate, and the count was 400 after 2 hours and 225,600 after 6 hours. So first, this is a multi-step problem, but first we want to know what is the relative growth, and that's going to be our first part, and it wants to know as a percentage. So that's just going to be moving the decimal around a little bit at the end. Well, we remember we're talking about a population again, so I think P of t will work good again for general formula, e to the kt, that's what we discussed before. And we know p of 2 equals 400. So these are all the things we know just up at the top here. Actually, let's change this to the blue, so this will be representative of what we know given what the problem says. And then we know p of 6 equals 25,600. So those are the three facts we know. So we can say that 400 equals p of 0 e to the 2k. And then we can also say that 25,600 equals p of 0 times e to the 6k. So those are the two equations based on the facts that we're given. So now the easiest way to go from here is to solve this kind of like a system. So first, we're going to solve equation, this will be called equation 1, that's equation 2. So solve E1 for p of 0. And we can easily do that such that p of 0 equals 400 e to the negative 2k. And now we can say, we can plug this value in, because we know p of 0, so p of 0 equals this, and we can plug that in for that other equation. So now we can say that 25 to the second plug so that's going to be 25,600 equals 400 e to the negative 2k e to the 6k. And from here we can divide out the 400, so divide out the 400 on both sides, so we have 25,600 over 400 equals e to the negative 2k times e to the 6. So we just got rid of that 400 term right here, we just divided it out. So now we're starting to get things a little bit simpler. Well, we divide that fraction there on the left, that gives us 64 equals e to the 4k. We're just combining these exponents, this exponent, and this exponent, we're just combining them together. That gives us e to the 4k. And now we use the property of logarithms like we discussed in previous sections and apply the natural log. So third is going to be apply ln. And that's going to give us ln of 64 equals ln of e to the 4k. Well, we know ln and e cancel each other out, thus ln of 64 equals 4k. Now, simple algebra problem, divide by 4 on both sides, and that's going to give us k equals ln of 64 over 4. And upon plugging this into the calculator, you get a decimal of 1.04, which equals 104%. So if you didn't have a calculator, that'd be a perfectly good stopping place, but if you do, then you get it exactly as the percent that they wanted. Question, and that's going to be right there. Now, second part for this problem, part B, is going to be what was the initial size of the population. So this is another parameter we're trying to solve. So we know that p of 0 equals the initial size. Now we're going to use the k value that we found in the previous problem to solve for p of 0. So we have 400 equals p of 0 e to the 3 halves ln of 2 times 2. That's another way of representing this term right here. So there's a little bit of algebraic manipulation. I'm not going to go through it in the interest of time, but that is equivalent to this term right there. Now we're just solving for p of 0. So p of 0 equals 400 e to the negative 3 halves ln of 2 of 2. So we have p of 0 equals 400 e to the negative 3 ln of 2. So we're getting rid of 2. So now we get p of 0 equals 400 e to the negative 3 ln of 2. Well, we know ln and e cancel each other out, so we can say p of 0 equals 400, canceling the ln and the e, times 2 to the negative 3. Remember get rid of ln, and then this 3 moves up to be an exponent. So that's going to be 2 to the negative 3. And then to evaluate that, we'll put that in the denominator. So this is going to equal 400 over 2 cubed. 2 cubed is 8, so 400 over 8 equals 50. So 50 was the initial population size. So we just, again, used what we found in part A and plugged that in to the problem here. And you could, just if you had a calculator, it'd be a little bit easier. You could refrain from simplifying this to that term there, and you could just plug this right in and it will work the same. Alright, so for part C, we want to find an expression. So find an expression for the number of bacteria after T hours. So our main goal for this is just to find a formula where we can plug in T. So find formula plug in any T. That's the main goal. So now that we found the initial population size and our K value up top, we're just plugging those in, and that's really all that's going on here. So P of T equals P of 0 e to the KT, that's the general formula. P of T equals 50 e to the ln of 64 over 4, and again you could write a simplified version in there. And that's going to be times t. So now all we have to do is plug in any t value there and there, and that's going to give you how many bacteria we have. So now the only variable present in this problem is a t, because remember e is a number. Don't make that mistake. So in this last part, we just want to find the growth rate after 4.5 hours. So that's going to be taking the derivative of our formula we found in the previous problem. So we want p prime of t equals d dt of that formula we found. So we want 4.5 hours. So 50 e to the, I'm going to write the simplified form here. So ln of 2t. That's going to be, I know that's different than what we put in the formula, but that's simplified. So we'll put that. And then equals 50, and then d dt e to the 3 halves ln of 2. Alright, so we know that's going to equal 50 e to the 3 halves ln of 2 times t times d dt of e to the 3 halves ln of 2t, because that's chain rule. So that just gives us 75 ln of 2 e to the 3 halves ln of 2 t, and that's the derivative. Now we have to plug in our time. So now p prime of 4.5 is going to be this right here, but with 4.5 in there for t. Then we calculate that. So 75 ln of 2 e to the 3 halves ln of 2 times 4.5. And that's going to equal 5596 cells per hour. So again, for this problem, we take our formula from before, and I know I've been a bit inconsistent with this, but this is just a different form of what I wrote in the formula, the exact same number though. Taking the derivative of that whole thing, take the 50 right out of there, and then we're taking the derivative of this term, which we know is done by chain rule, so 50 times this, times the derivative of that, which is calculated, and then we add we do the 75 times the derivative of this, and then that results in this term right here, and we're just plugging in 4.5 right here into that formula, which gives us this number there, and that's how many cells we're putting on. So for the last example we're going to look at, we know the half-life of radium-226 is 1,590 years, and we're just going to denote that by t of 1/2 equals 1590, so that's just an easy way to label that. And then part A, this is a three-part question, but part A is saying a sample of R226, I'm just abbreviating here, has mass of 100 milligrams, and we want to find a formula for the mass of the sample remaining after t years. So we know that the original mass has an original mass of 100, and that reminds me of that formula we've discussed previously in the other problems. And we're going to denote that as m of 0. So I know we've talked about like k of 0 or p of 0. We'll just denote this as m of 0. It means the exact same thing, but we're just denoting it differently to make it appropriate for this problem. So m of 0 equals 100 milligrams. This time we're just going to use the formula, but it's going to be a little bit different because we're dealing with a half-life, and we want to know how much remaining after a certain number of years, and we know the half-life. So we could say the 1/2 m of 0, so half of the mass left, that's the half-life, equals m of 0, which is the original starting mass, times e to the k times t 1/2, which is the half-life. Okay, so now we can just say 1/2 equals e to the k times 1590, because the half-life is 1590, and we're just canceling out the m0 terms right here. So now we're left with this, which is fairly simple at this point. So we see e2, and it has an exponent there that indicates we need to take the natural log of both sides, so ln of 1/2, this should be a review from pre-calc, equals ln of e to the k times 1590, and then we know ln and e are canceling each other out, so we have ln of 1/2 equals k times 1590, and we want to know k. So we'll just divide both sides by 1590. We cross out on that side, and therefore k equals ln of 1/2 over 1590. And therefore we can plug this back into the original equation. So and this is going to be the formula we've discussed before, and now we're denoting it m of t equals 100 e to the ln of 1/2 over 1590 t. So that's our whole entire k value right here that we just found, and that's being plugged right into that formula. This whole form right here should look similar to the formula we discussed previously. And that's going to be the answer for part A. Now for part B, we want to find the mass remaining after 1,000 years. So find mass after 1,000. And it wants it correct to the nearest milligram, correct to the nearest. So we know that m of 1,000, we're just plugging 1,000 into t, so looking at our previous equation, we're just putting the 1,000 there and then the 1,000 up there. So m of 1,000 equals 100 e to the ln of 1/2 divided by 1590. Remember that whole term there is k times 1,000. All that's in the exponent. And remember the properties of natural log and e. We're canceling those out, so ln and e cancel. Now we're just left with e 100 times 1/2. 100 over 159, and that's going to equal 65 milligrams after elimination. And that's the total number of mass remaining after 1,000 years. So again, it's just utilizing that formula we've gone over several times and manipulating it to fit this problem. For the final part here, we're going to be looking at C, and that asks, when will the mass of this sample be reduced to 30 milligrams. So that's what it wants to know. After how much time? So it's asking about time here. And we'll just note that. So we want t, so 30 equals m of t. Therefore, we can just, because we want 30 milligrams to be our answer, so to say. As such, 30 equals 100. We're just replacing m of t with 30. E to the ln of 1/2 over 1590 times t. And now we can rewrite that as 30 over 100. We're just dividing out the 100 here, dividing it over here, cancels. Equals e to the ln of 1/2 over 1590 times t. So now we just have to take ln of both sides to cancel out the. So we have ln, and we're going to simplify 30 over 100, it'll just be 33 over 10, equals ln of e to the ln of 1/2 over 1590 times t. Ln and e cancel, we have ln of 3/10 equals ln of 1/2 over 1590 t. And therefore we just want to divide ln of 1/2 over 1590 on both sides. It's just a very complicated algebra problem. With the term we're dividing there such that those cancel out. Now we're just left with t by itself on the right hand side. We'll switch the sides so that we have 1590. Remember, multiplied by the reciprocal here. 1590 ln of 3/10 divided by ln of 1/2. We put that in the calculator and we'll get our total number of years, which is 2,762 years. And that's the final answer for this problem. And that concludes our topic on exponential growth and